hints until we had these kinds of maps more recently. In addition to the South Pole Aitken Basin, you can see at the equatorial part of the far side of the moon, we have our highest topography, again up to about 8 kilometers above the agreed on datum. The topography of the moon is largely bimodal. In other words, you're either on the rough, lighter colored highland areas or the smooth, darker colored Maria. When we consider roughness, we're really talking in most cases about whether it's mountainous or not mountainous, and those are big scale things in terms of the terrain. But it's also important to consider whether we have roughness at a human scale, or in the case of going back to the moon, on a lander scale. And the highland areas turn out to be actually smoother at a lander scale, and the Maria are rougher at the lander scale. Lunar landforms are dominated by cratering. We talk a little bit about lava flows, but even the lava flows are affected by cratering because the lava flows are found filling craters. There are literally thousands of impact craters, ranging from the size of the South Pole Aitken Basin, which is 2,500 kilometers across, to the zap hits, which are microns across. The shape and form of an individual crater changes as a result of two things. One is the size. The larger craters tend to be flatter floored. The smaller ones tend to be more bowl-shaped. In addition to that, as a crater spends time at the lunar surface, in other words, it goes from being a young crater to an older crater, it gets more and more subdued until finally it's just barely there. Unlike the Earth, the terrain on the moon is not dominated by plate tectonics process. It is solely a function of where things have impacted and the volcanic events that have filled those areas. In any event, completely smooth, flat areas on the moon are rare. They occur in the Maria, but the Maria are fairly old, so they have been broken by numerous craters as well. The slopes in the Maria are around 4 to 5 degrees on average, so it's not very steep terrain, although as you can see the crater in the center of this picture, if you get close to a young crater, the terrain gets quite a bit steeper. The Highland Maria boundary is generally sharp and abrupt, much as we see here at the Apollo 15 site in the Hadley-Apennine region. Because of that abruptness of the boundaries is again why we see the dark Maria areas. If those boundaries were not abrupt, the Maria would not have that sharp, obvious image on the moon's surface. The highland terrain consists largely of rolling hills, some of them quite high, but nevertheless not jagged, steep cliff faces like we see on terrestrial topographies. The highland terrains are created largely by overlapping ejecta blankets from large craters. If we get close to a young crater, for instance like Tycho, the terrain is quite rough. But away from the young impact craters, the average slopes are 7 to 10 degrees, but the scale of the topography at, let's say, a lander image or a lander footprint is quite smooth. Surface lighting is something that not only we dealt with on Apollo, both in terms of operating on the lunar surface, but also seeing the topography for crews to land at, but also we'll be worried about it when we go back to the moon because we're there to stay. Apollo 12 had the shallowest sun angles, so 7.5 to 9.5 degrees, very shallow. Apollo 16 had the highest sun angles, 45 to 48 degrees. On the left is an Apollo 12 picture on EVA-1. You can see how long the shadow of the lunar module and the astronaut is. On the right is the Apollo 16 site at the highest sun angle. And in contrast, the surface is much brighter, the shadows are smaller, and in general, it's harder to see your way around on the terrain in high sun angles than it is in lower sun angles. Anybody that's ever been skiing in flat light knows that you can ski off some remarkable terrain that you didn't even see because the shadows aren't there. In some ways, driving around on the moon in high sun angles is going to be similar to that, and possibly when you drive, you're going to have to be tacking back and forth down sun. These are two pictures essentially looking up sun and down sun, Apollo 12 EVA-1 down sun, the sun is 7.5 degrees, so you can see if you're looking directly down sun, you don't see much, but if you look to the right or to the left, you can see quite a bit. And that's what I mean about having to tack back and forth around the sun. If you want to make sure you don't drive into something that's exciting, you're going to have to be careful how you drive. In contrast, Apollo 17 EVA, sun's about 16 degrees, and that's looking up sun. The terrain is somewhat easier to see, but it's still glaring sunlight when you're going directly into the sun. A unique aspect of working on the lunar near side in the dark is illumination by earthshine. Because the moon's orbit is locked and we always see the same face of the moon, the Earth always stays in the same spot in the sky. And when you have a full Earth, it's something like 80 times brighter than a full moon. At essentially lunar midnight, if you're out working under the Earth with a full Earth, it's as bright as about 8 o'clock on a summer evening on the Earth. So the reality is that when you're out at night in Earthshine, you'll be able to see just about everything you need to without artificial illumination. John Young once told me that not only was it bright enough to see the lunar surface from orbit with Earthshine, you could actually tell color differences and see individual craters with Earthshine. So Earthshine is going to be an asset that's really important for future lunar operations, unless, of course, you're on the far side. The far side, the Earth is never in view. So when the sun goes down on the far side, with the exception of starlight, it's going to be really dark. In addition to that, when we're working at the poles, because the sun is so low to the horizon and the Earthshine is so low to the horizon, you're almost always going to need some level of illumination so you just don't step into dark holes because of the low sun angle. Let's talk about regolith. Regolith is one of those aspects of the lunar surface that has received a lot of discussion over the years. There will be a further lecture just on regolith, but I want to touch on it here to give you an idea of what it is. The basic definition of regolith, and this is a geologic definition, is the layer or mantle of loose, unconsolidated rock material of varied origin that rests on bedrock over most of the lunar surface. In other words, regolith is what happens if you take bedrock and just beat it up until it's just nothing but fragmental material. We use we use regolith on the Earth to talk about soils as well, but the moon is essentially just plain old rock. The regolith can be formed in place or it can be transported from adjacent locations. Generally speaking, if you pick up a handful of regolith at any one spot on the lunar surface, roughly 90% of the material in your hand is going to have been derived very locally. About 10% will have been transported in by meteorite impacts from other locations. There are a lot of processes that affect regolith formation. Obviously, the principal one that creates regolith is meteorite impact. It breaks up the bedrock into all sizes, and the variety and sizes of meteorites create variety and sizes of regolith. In addition to that, we have cosmic rays, we have solar wind, and those create variations in the regolith which have caused it to be quite different at a very, very small scale, and I'll leave that discussion to the subsequent lecture. The median particle size of regolith is about 40 to 130 microns. That's really small. And it's much smaller than we experience, for instance, when we're at the beach. 95% of the regolith is less than 1 millimeter, and if you're out the beach, the roughly average size of the sand is about 2 millimeters. So the moon is not going to be like a day at the beach. There are a lot of things in the regolith. There's a lot of things mixed up. It's ground broken rock, it's impact melt, it's bits and pieces of meteorites, so it's very variable. The graph shows the variation in the nature of the regolith at various landing sites, in this case, surveyor landing sites. And you don't need to take away real detailed specifics on this, but it's important to recognize that the regolith isn't the same all around the moon. As the surface gets older, In other words, it's been exposed to the lunar, at the lunar surface for a longer period of time. It changes grain size, it changes character. So every landing site will be slightly different. When we landed the lunar modules on the regolith, we had a variety of essentially interactions between the regolith and the lunar module. First thing, of course, is everybody knows that down close to the surface, the astronauts saw dust moving around. And if you look at the upper left picture and the lower left picture, those are sort of striations, little ridges and troughs created in the regolith by the ejecta, by the exhaust from the lunar module. If you look at the upper right picture, you can see that in that case, the regolith was quite fluffy and the foot pad sank, probably 1 to 2 centimeters into the regolith. On the lower right picture, you can see that, in fact, the foot pad is just sitting on the regolith. So how compact and how fluffy the regolith varies from place to place. But none of it, in no place, is that fluffiness deeper than about 10 centimeters. There's been a lot of discussion about dust and what it does to astronauts and hardware and rovers and spacesuits and things like that. The picture is of Gene Cernan after EVA-3 on Apollo 17. He's just pulled his suit off, and you can see that he's got a lot of dirt on his face, not because the regolith came into the suit during his EVA, but because the suits, which you can see piled on the ascent engine cover in the background, were pretty dirty from walking around on the lunar surface. There's been a lot of discussion about levitated dust. There's been a lot of discussion about whether dust is a critical design issue that will cause failure if it's not followed or not paid attention to. Levitated dust has been suggested both by the horizon glow taken on the surveyor cameras and by photographs and notes made by Gene Cernan as the Apollo 17 command module approached the terminator. There's been a lot of discussion, is dust levitated? Does it move around on the lunar surface? There's a couple of things we can look at to try and get some idea of whether there is a large-scale transport of dust on the surface. The first is that Apollo 11, 14, and 15, we put laser retroreflectors on the surface. Now, these were corner cube reflectors that were designed to reflect laser light back to the Earth. So if there's dust moving around, you would really expect those corner cubes to get covered. And even if they're not completely covered, you would expect to see some reduction in the signal strength coming from the moon over time. The Apollo 11 retroreflector has been on the moon now for over 48 years. The others somewhat less time. There has been no evidence of any degradation in laser signal over the lifetime of these arrays. So if there's dust moving around, it's not covering the retroreflectors. When we went to the moon on Apollo 12, we landed near the Surveyor 3, which had spent 31 months on the lunar surface prior to the arrival of the Apollo 12 crew. Although there was some dust coating on parts, the patterns on the coating indicated that the dust was blown onto the Surveyor either by the lunar module landing or by the engines of the Surveyor itself. Again, there was no evidence of dust having settled on the spacecraft from any other source other than the engine exhaust. In fact, there was even a study published where a research team looked at the Surveyor parts brought back to the Earth, and they saw no evidence that dust was on these parts except by blown on by the engine bells. Now, when we establish an outpost, because engine bells do blow dust around, we're going to have to be careful about where we land our spacecraft so that we don't spray dust all over our habitats, deployed equipment, and instruments on the surface. So in that case, we will have to accommodate the fact that if you have an engine coming past the surface, it's going to blow dirt around. There's been some discussion also about whether dust is moving in the Terminator. When the Terminator comes by, there's some suggestion that there are variations in the electrical current, which some people have suggested would cause dust to levitate. So I want to talk a little bit about that particular issue as well. And this concern was raised before Apollo, And Apollo, I think, provides us some pretty conclusive proof that it's not happening. The first, I think, that's really important is that the albedo gradients between the highlands and the mare, the highland rocks being lighter colored, the mare rocks being darker colored, are sharp and distinct. They're preserved at remote sensing scales, they're preserved at photographic scales, and the crews on the surface could see them. In the upper right, or the right, is a picture of the Apollo 17 site. You can see very clearly that the highland terrains are distinct from the mare fill in the valley. At the left, you have a geologic map from a publication in 2002 that shows, by using remote sensing data, that those albedo variations indeed represent compositional variations, and that there is no sense that there's a homogenization of the lunar surface from dust. Likewise, if you go up to orbital altitudes and look at things like the mare highland boundaries, in this case Mare Crisium, on the left you see the albedo picture, on the right you see the iron map, and again, you can see clearly that iron does not bleed over into the highland terrain, that the boundaries, the albedo boundaries, are as sharp in the remote sensing data as they are in the visible light. LADEE was a spacecraft I talked a little about earlier as having been sent to the moon recently to look at whether there was a dust component in the high altitude lunar exosphere. And in fact, LADEE saw, while there was some tenuous dust, there was no evidence of electrostatically lost dust at high altitudes. Lastly, if a lot of dust was moving around, we would expect the rocks at the surface to be either covered in dust or at least have a mantle of dust. And there is no evidence on rocks that have been essentially exposed to the surface for hundreds of millions of years of any accumulated dust blanket. We conclude that lateral dust transport on the moon, if it happens at all, is very inefficient and is not coating the lunar surface with new dust every time the sunrise goes by. Let's talk briefly about the origin of the moon. We'll get into more detail in subsequent lectures, but there were three traditional modes that were advanced prior to Apollo. Some of these modes date back to literally Charles Darwin's grandfather. The first was what we call the fission model. The idea was that early on in the history of the Earth, when it was largely molten, and if it was rotating fast,